Okay, so good morning, everyone. First of all, let me thank you all for attending this presentation today, and especially the members of the Thesis committee. Despite the circumstances, we'll try to make our best for carrying out the presentation as smoothly and normal as possible. So my name is David Roca, and I'll be presenting the defense of my PhD thesis entitled Numerical Tools for the Computational Design of Acoustic Metamaterials. To start, I wanted to briefly show you how this thesis will be structured. As you may have noticed from the title, the topic of the thesis is acoustic metamaterials, and the methodology employed to study and characterize them is through numerical and computational tools. So I'll dedicate this first section of the presentation to introduce the concept of metamaterials, and in particular acoustic metamaterials. And then I'll proceed to present the currently available computational techniques, focusing on which ones have been used in the context of the present thesis. Then I'll move on to the scientific contributions, and since this is an article-based thesis, I've structured the section into 3 subsections, so that each subsection corresponds to each of the 3 articles that have been produced through the development of the thesis. So in this first subsection, I'll talk about the multi-scale homogenization framework that is proposed in the first article. Then I'll talk about how this model has been applied to the design of acoustic metamaterials. And I'll end with the experimental validation of the proposed model, which corresponds to the results of the third article. And as a conclusion for the presentation, I'll make a brief discussion on the results, and then I'll talk a little bit about the current and future research line derived from the work developed in this thesis. Okay, so let's start with the state-of-the-art section. And first of all, let's answer the question, what are metamaterials? Even though the idea behind the concept of metamaterials was discovered decades earlier, the proper use of the term metamaterials was introduced in the late 90s. So let's first have a look at what is the etymological meaning of the term, which comes from the combination of the prefix meta, which is translated as beyond, combined with the word material. So in this context, this word construct gives us the notion that metamaterials can be understood as materials with properties beyond those found in nature. This somewhat informative definition can be translated into a more technical language by describing metamaterials as artificially engineered materials to make them capable of manipulating weights with a specific purpose. In other words, we can define them as materials whose microstructure has been altered to make them have certain interesting properties. Note that this definition refers to waves, but not any specific kind of waves, as the idea can actually be applied, for instance, to electromagnetic waves, which is actually the field in which the concept was born as a means of building materials that exhibited negative refractive index. But in the topic concerning us, these waves will refer to acoustic waves. And in the next slides, I will talk a little bit about what is the physical background behind this kind of materials and for which kind of applications are they interesting. But first, and just for context, I should explain that in the field of manipulating acoustic waves, there are typically 2 similar and yet different concepts to explore, which are phononic crystals and acoustic metamaterials. In these figures here, I show what is a unit cell in an infinitely repeating structure for these 2 concepts. In both cases, we find different masses attached to one another, but in the acoustic metamaterial case, we notice that there is one of the masses attached inside the other mass, while in the phononic crystal case, the masses are sequentially attached to one another. And this intrinsic distinction in the unit cell composition translates in different dispersion behavior, as it can be appreciated in these dispersion diagrams. You should notice that in both cases, these two concepts are capable of producing what are known as frequency band gaps, which are regions in the frequency spectrum where wave propagation is effectively stopped, which translates in practice with huge levels of attenuation in these frequency ranges. And we notice here two important differences with these two concepts, that for a comparable wave propagation speed in static conditions, we notice that the band gaps produced in the phononic crystal case typically occur at higher frequency ranges, but these band gaps tend to be wider, while in the acoustic metamaterial case, these band gaps are more narrow band, but they appear in lower frequency ranges. In fact, it's this ability to operate in these low frequency regions which make the acoustic metamaterials appealing for several kinds of acoustic applications. It is well known in the acoustic fields that we have two main standard ways of attenuating noise, which is either through high mass or through damping mechanisms. Damping mechanisms are effective in high frequency ranges, where we can find a large collection of solutions. But to tackle the low frequency range, one is typically forced to resort to mass. And that is not always practical or even feasible. For instance, in aerospace context, having extra mass is very critical. So the idea of or the possibility of having a material which is both lightweight and at the same time can deal with undesirable specific noise sources in the low frequency region is very appealing and interesting. Now, in order to understand a little bit more what is the phenomena that gives these acoustic metamaterials their interesting properties, we should have a look at their internal structure. Notice here that we have different inclusions, which actually are resonating elements, typically characterized by a resonance frequency, so that when an acoustic wave, when the material is subject to an acoustic wave at a frequency in the vicinity of the resonance frequency of these internal resonators, they obviously start to vibrate, and in doing so, they capture energy from the propagating wave, so that when it reaches the other side, its amplitude has been drastically attenuated. As I said in the beginning of the presentation, the notion of metamaterial has been present since the late 90s. But in the particular case of acoustic metamaterials, the first actual realization and the demonstration of this local resonant effect was found in 2000. Since then and throughout the years and up to the present day, the concept of local resonance has been studied and several different configurations have been proposed in the literature. Just to have a look at a few examples, we can find, for instance, what is the classical design of an acoustic metamaterial, which consists of a composite material in which we have a structural element, typically a polymer, hosting the resonators, which in this case are in the form of metallic spheres coated with a rubber material. But this idea has evolved throughout the years in order to tackle different or more specific kinds of applications. For instance, in this case, we find hollow cavities in which the resonating element here is actually the air inside this cavity. So they are typically applied to applications in which airflow is relevant, for instance. We also find these other kinds of applications in which the focus is put on tackling in-plane wave propagating through the plate. And in this case, the vibration of these small pillars would be the one triggering local resonance effects. And we end up with more recent concepts, which are 3D printed, for instance, panels, in which rather than relying on the combination of material properties in order to achieve the local resonance effect, we resort more to the geometrical and topological shape of the resonators. Okay, so after this brief introduction to the topic of the thesis, let's now have a look at the methodology employed. And in this regard, the use of computational tools has been considered appropriate, since it allows us to properly deal with the somewhat complex and sophisticated structures that typically constitute the internal topology of metamaterials. And in this particular thesis, we have focused on the three main pillars of the computational design of materials, which are the multi-scale modeling, which is a family of techniques that is employed to retrieve a set of effective properties of materials which show two differentiated scales, so that through these effective properties arising from the microscale, we're able to analyze the effective behavior in the macroscale. We also find model order reduction techniques, which allow us to alleviate the computational cost associated to large-scale problems. And finally, also topology optimization algorithms, which can be used in a later stage to assist in the design process of such kind of materials. For instance, in this case, by designing what would be the shapes of the inclusions in the acoustic metamaterial unit itself. As for the models actually present in the literature, we find that variational formulation and interscale energetic equivalence have been present for many years, but in static context. And it wasn't until 2015 that these homogenization schemes were generalized to also deal with inertial effects. On the other side, acoustic metamaterials have been more typically studied in analytical ways, and the only computational models have focused on the analysis of the unit cells, specifically for deriving their dispersion properties. So in an attempt of combining both worlds, we have thought of implementing these novel homogenization techniques to study the acoustic metamaterials not only on the unit cell level, but also in a more macroscopic setting. And in this regard, we find this work here, which I would count among the first, in which they combine these two models. And we also would find the contributions of the present thesis that I'll explain later on. And also to have a quick look at different works in the literature tackling acoustic metamaterial design, we found works in which topology optimization is performed to obtain optimal configurations for tackling multiple resonance peaks in the acoustic metamaterial, and also works in which other attenuating mechanisms are combined with local resonance in order to try to increase the attenuating performance of acoustic metamaterials. In particular, we have the work from Hussein, in which he introduces the concept of metadamping, which combines the local resonance with dissipation effects, and also this work in which the notion behind, or the phenomena behind phononic materials, which is this Bragg scattering phenomenon, is combined also with local resonance in order to try to enlarge the frequency bandgaps. Okay, so let's now move on to the scientific contributions of the thesis. And let's start with the results from the first article, in which a multi-scale homogenization framework is proposed. For context, let's imagine that we have a macroscopic body in which we are able to clearly identify a lower scale, this scale being identified with a representative volume element. In cases where periodicity is present, we can also identify this representative volume element as a unit cell. And then we'll simply apply the standard balance of linear angular momentum, so that we will assume that the typical equations of motion are satisfied in the context of a small displacement and strains. And we will link each point in the macro scale to a specific RV in the micro scale through an energetic equivalence, which is postulated in this case as the so-called multi-scale virtual power principle that was first proposed in the work from Souza in 2015. And basically what we are doing here is establishing that the total mechanical energy in this specific macro scale point needs to be the same as the volume average mechanical energy of the corresponding RV. So in order to close the problem, a kinematic connection needs to be imposed between both scales. And in this case, is stated as a first order expansion of the displacement field plus a so-called microfluctuation field. While the appropriate choice of this kinematic restriction is important in order to properly capture the effective behavior of the microscale, here I show what are known as minimal kinematic restrictions because they will be useful in the derivations that follow. I would like to point out here that these marked blue terms appear in order to account for inertial effects. So if they weren't here, this whole formulation would be equivalent to the classic homogenization models for static problems. And I also want to point out that in the derivations that follow, I will be neglecting the effect of body forces, even though they can be accounted for and the derivations are equal if we account them as an effective D'Alembert force vector that would include these body forces along with the inertial forces. But for simplicity and clarity in these and the derivations that follow, I will be neglecting these body forces. So the statement of the energetic equivalence is shown here in variational form as the generalized Hill-Mandel principle, which combined with the set of minimal kinematic restrictions allow us to choose some arbitrary displacement gradient, and microfluctuation fields that allow us to obtain a set of upscaling relations, which actually give us expressions for the effective macroscopic inertial force density and the effective macroscopic stress. We can also derive a restricted RV variational problem from which the microfluctuation field can be solved in terms of the macroscopic displacement and strains, which are introduced in the system through the kinematic restrictions. So even though this variational problem, along with the kinematic restrictions, gives us a way to actually solve the problem, we will express it as a saddle point problem by introducing these Lagrange multipliers associated to the minimal kinematic restriction, so that now the microfluctuation displacement field is totally unrestricted. What's interesting about this choice of for the Lagrange multipliers is that we are actually able to identify them as the effective macroscopic stress and the effective macroscopic inertial force density. By making them appear explicitly in the system, and since we are able to give them this physical meaning, we gain the ability to use them to justify certain simplifying assumptions in the system resolution. In particular, since our intention is of using this model for the resolution of acoustic metamaterial problems, the following set of assumptions will be considered from now on. First, the body forces will be neglected, which we've been doing so far already without any relevant consequence in the formulation. Then the macroscopic strain acceleration field will be considered small. This assumption is actually very important because it limits the applicability of our model to cases where the separation of scales condition is satisfied. And since this is an important aspect in the formulation, I will be dealing with it in the next slide. Then it will be also assumed that the material distribution in the RV is symmetric with respect to its geometric center, which serves as a simplification, which allows us to neglect the possible effects of micromoments in the microscale, which are actually not really relevant in many acoustic metamaterial settings, since the kind of excitations that would trigger these micromoments are not typical in acoustic wave propagation. And finally, since most acoustic metamaterial structures are periodic, a more appropriate set of kinematic conditions will be used for the microscale displacement field. In this regard, the microfluctuation field will have a standard periodic boundary conditions, and the rigid body motions will be prescribed at some points in the boundaries to avoid relative motion of one unit cell with respect to the other. This set of conditions has already been used in this other work, in which they also propose a homogenization scheme for acoustic metamaterials. And in this regard, we thought that they would be appropriate also in our context. Okay, so the separation of scales condition in acoustic problems can be translated in terms of frequencies by limiting the applicability of the model to frequencies below those triggering the first deformation modes of the unit cell. This is actually also a condition for local resonance phenomena to arise, so it actually works for our purposes. Notice, for instance, that for a typical unit cell configuration, the first deformation modes would appear at frequencies around 10,000 Hertz, while the internal modes triggering local resonance effects appear at frequencies an order of magnitude lower. So our model would be capable of capturing this, since they satisfy the separation of scales condition. Now, to proceed with the derivation, we will express the extended RV system, including the Lagrange multipliers, in matrix form after a standard finite element discretization is performed. After that, the system is split into a quasi-static and inertial component, in which we take into account different components of the action vector separately. Taking a look at the quasi-static subsystem, we quickly realize that since the only source of excitation is a macroscopic deformation, and as established by the hypothesis that we made earlier, their inertial component is neglected in virtue of the separation of scales condition, then the system can be reduced to the classical homogenization case, from which the macroscopic stress is related only to the macroscopic strain through this fourth order effective constitutive tensor. The second subsystem here deals with the inertial part of the system, and since now the only excitation comes from the macroscopic displacement, in virtue of the hypothesis of the symmetric density distribution on the RVE, we can neglect the micromoments contribution on the resulting macroscopic stress tensor, which is this term here. And since the excitation is actually a rigid body translation type, the resulting stress reaction expected can also be considered negligible. So the system reduces to this one, from which the expression of the macroscopic inertial force density can be derived in terms of the macroscopic acceleration field and a microinertial component coupled with this microscale system. It is important to notice that the resulting inertial system in the microscale needs to be solved at each time step, and so the total number of degrees of freedom ends up being the same as if we intended to solve the whole microscale through a direct numerical simulation, granting the whole multi-scale model computationally useless. And to overcome this issue, a model projection onto the only relevant modes of the microscale is performed, so that the total number of degrees of freedom in the coupled system is drastically reduced. In order to select these appropriate modes, there are typically two aspects to consider. The first one is the separation of scales condition, which automatically allows us to discard those modes above the frequency limit imposed by the first deformation modes. And second, Not all the remaining modes are capable of triggering local resonance effect, as only those with non-negligible values in these coupling matrices have an actual effect on the macro scale. In the end, we get that typically only 1 or 2 additional degrees of freedom ends up being relevant. So this reduction strategy is actually very effective. This slide here shows an schematic representation of the whole multi-scale model. Starting with the wave equation in the macro scale, the macroscopic displacements and strains end up becoming actions in the RV system, which is split into a quasi-static component from which a macroscopic stress can be obtained, and the inertial component from which, after performing a modal projection, we obtain an expression for the effective inertial force density with this coupling terms through these modal amplitudes with the microscale. Okay, so having established the homogenization scheme, let's now apply it to the specific case of panels for acoustic attenuation. And in doing so, we'll explore some design configurations for the unit cell and how we can try to improve its performance. So first, the problem that we'll be solving is the computation of the transmission loss of a panel. The panel is composed of a collection, a periodic collection of unit cells, and it's surrounded by air on both sides. In this side, we will have incident and reflective acoustic plane waves. And in the other side, we will only have a transmitted plane wave propagating. And then to solve the problem, first we will retrieve the effective properties of the unit cell by employing the homogenization scheme that we described earlier. And we will use these effective properties to study a homogenized panel slice of the macro scale, from which the transmission coefficient will be obtained. The analysis will be performed on the frequency domain, but the formulation would allow for it to be solved also in the time domain if transient effects were also to be of interest. Okay, so the composition of, well, the typical composition of the unit cells that will be considering is actually made of 3 different components. First, we'll have a matrix that hosts the resonating elements and has the purpose actually of isolating the vibration of each unit cell. So in this regard, ideally we want this matrix to be relatively stiff. And then we'll have the resonating elements, which typically include resonant inclusion, and an element that needs to act as an effective spring, which in this case is this coating phase. And in order to tackle our target frequency range of interest, we will want these resonance inclusions to be as dense as possible, while the element acting as spring will want it to be as compliant or as flexible as possible in order to achieve these low frequency ranges. Throughout the development of the thesis, different unit cells configurations have been considered. We've also talked about this composite classical one. Here we have a similar concept, which is also a two-dimensional setting. But in this case, the coating phase is substituted by this small, let's say, strings connecting the inclusion to the matrix. And in this other case, which is of more three-dimensional character, it's composed of a single material phase, and the motion or the vibration of the unit cell is in the out-of plane in this 3D character. As for the materials that will be employed, you can see here that we have used typical or common materials in the polymers family. The metals family we have considered steel, and in the rubber material family we have considered also a common silicon rubber. So in the first article, an analysis for this unit cell is performed in order to numerically validate the homogenization model. And these are the resulting RD modes for the free system, which is a system with no kinematic restrictions, and the system with the appropriate set of kinematic restrictions. The modes and frequency in both systems will be relevant to establish the dispersion properties of the design, as we will see in the next slide. But first, I want you to notice that these modes here can actually be already discarded, because as you can see, their coupling matrices terms are actually null, so they will have no effect on the micro scale. And since our frequency range of interest is below the 10,000 Hertz, actually our only relevant modes will be the first one. So in this case, we will have an additional degree of freedom in the macro scale, the separation of and the reduction strategy is very, very efficient. These plots here show the dispersion properties of this specific unit cell design, and I want you to focus on the appearance, as expected, of this frequency bandgap here, which is actually related to an effective negative density. I mean, the material behaved in this frequency region as if it had a negative density. But what I want to point out here is that the limits of this frequency bandgap actually correspond to the natural frequencies for the restricted and unrestricted RV systems, which is something that we'll be using later on in the design process. So upon computing the transmission loss and comparing the results with direct numerical simulation, we can see that our model agrees very well in the frequency range of interest. And we can actually have a bit of insight in the applicability of the model, since we see here how the results start to disagree as the frequency increases and approaches the separation of the scales limit. Now we'll think about different ways or different strategies to try to enlarge the frequency range of attenuation. And in this regard, a first idea emerged consisting of combining two layers with a slightly different unit cell configurations so that their corresponding band gaps overlap. The resulting attenuation band is not exactly the superposition of the two due to interface interaction between both layers. And we actually see here these inverted transmission peaks, which are undesirable in some contexts. However, it manages to obtain a larger combined bandgap in a lower frequency region, which is always desirable for the kind of applications expected. Then we had another idea to exploit the dissipative nature of certain materials in order to combine damping with local resonance effects. This motivated the introduction of damping in the homogenization model through this additional term in the definition of the microscale stress field, which now accounts also for damping through this viscosity fourth order tensor. So the consideration of this additional term implies the appearance of this damping matrix, but it doesn't alter or doesn't violate the assumptions previously made for simplifying the resolution process. And most noticeable differences that we can observe here is that from the quasi-static subsystem, we'll now obtain an expression for the macroscopic stress, which will include this effective viscosity tensor, which is intuitively expected. And on the inertial component, things get a little bit more tricky because upon performing the model projection, we'll now have this damping matrix which depending on the specific viscoelastic or desiccation model employed, it can actually have non-negligible diagonal terms, which puts at risk the whole reduction strategy. But we have studied this issue in our typical problems of interest, and we noticed that even for sophisticated viscoelastic models, the coupling terms in this matrix are very, very small. So it doesn't actually put at risk the whole reduction strategy because they can be neglected without further sacrificing the accuracy of the model. So a final option that was considered for improving the performance of the acoustic metamaterial design is or deals with the introduction of topology optimization. And in this case, we will be considering again our classical concept with three material phases, in which now the matrix component will be fixed. So our design domain will actually correspond to the shapes of the inclusion in this coating material phase. And we will tackle two different design goals. The first one being the localization of the frequency bandgap to a target frequency range, and then the maximization of this bandgap, which we will take advantage of what we saw previously, that the limits of the bandgap are actually related to the resonance frequencies for the restricted and unrestricted RV systems. So the topology optimization strategy employed is based on the computation of a level set function, the sign of which determines the region with inclusion material and the regions with coating materials. And the algorithm will advance following the Hamilton-Jacobi approach, through which a specific cost function is defined and its derivative with respect to an infinitesimal change in topology is evaluated in successive pseudo-time steps until a minimum value is reached. We'll see an example of how this algorithm actually causes changes in the topology. But first, let me show you with what is the cost function that will be tried to minimize here. Since we have two different design goals, we'll have two different components of this cost function. This one trying to match the frequency of the first relevant frequency for the restricted system to a target one. And this other one trying to enlarge the bandgap width through maximizing the difference between these two frequencies, which we saw that they mark the limits of the bandgap. So here we find the evolution of the topology throughout the optimization algorithm when only the frequency fitting component of the cost function is activated. We see that we start with the RV filled with material, and as the algorithm progresses, it starts removing material to give shape to the inclusions. And it is worth noting this sudden change in the frequencies, which is caused when the inclusion is detached from the matrix because of the high contrast between the stiffness of the materials considered for the inclusions and the coating. And now we'll have a look at the evolution on topology when also the bandgap maximization in the cost function is considered. We'll see that it starts the same way as before by removing material, inclusion material, causing this detachment of the inclusion. And we will see that now the frequency bandgap is actually enlarged by removing remaining material within the matrix space, because what this optimization algorithm is trying to do is concentrate the higher mass in the inclusion, because This is what actually makes the attenuation more effective. Here we can appreciate the results and how the effective attenuation band in the transmission loss diagram is actually increased when the maximization of the band gap is considered in the optimization process. In this case, by a factor higher than 1.5. And we also notice in these pictures the effect of dissipation, which basically tries to smooth the peaks in these curves. And up to a certain degree, we actually see that it has a beneficial effect, slightly increasing the effective attenuation band. But if dissipation becomes too high, it ends up killing the local resonance effect. So it's somehow undesirable from the acoustic metamaterial point of view. Finally, the last contribution of this thesis comes from an experimental validation of the local resonance effect in 3D printed prototype. And our goal in this case was to validate both the concept of local resonance and at the same time we wanted to see if the experimental results agreed well with our homogenization model. And also as a side objective, we wanted to design a prototype that could be built entirely by a 3D printing technique. This means that only one material was allowed in the design, and so the topology or shape of the unit cell needed to play an important role. The challenge is that typical 3D printing materials are too stiff to allow resonant frequencies in the low frequency region we wanted, which was around 1000 Hertz. So for it to work, we included these rod supports that are actually attached to these homogeneous skin plates to fix each unit cell and allow the internal modes to arise. And then in order to reach a frequency that low, we consider this flower-like design, which acts as a sort, which maximizes the amount of resonating mass, and at the same time makes these strings long enough so that their bending stiffness is low enough to tackle the frequency of interest of 1000 Hertz. The experimental test consisted of an impedance tube from which the transmission loss of a sample can be obtained. The setting consists of two tubes, one with an anechoic termination to avoid reflections, and the other with a loudspeaker whose purpose is to generate acoustic plane waves. As you can see, there are 4 microphones placed at different locations in the tube to measure the acoustic pressure at this point from which the transmission loss can then be computed. The tubes were specifically designed and built by ourselves with a specific set of dimensions to operate in a range of frequencies between 500 and 2000 Hertz. And I would like to highlight here the contribution of my father in this endeavor because he was who actually built the tube structure, and because without his help it wouldn't have been possible to perform these experiments. So I feel kind of obliged to acknowledge his invaluable contribution here. And having a look at the results, we can observe in this figure that from the experimental side, we have 3 different curves corresponding to the acoustic metamaterial, which is this curve here. And when we compare the results with 2 homogeneous panels with an equivalent thickness and an equivalent mass, we actually find that we have an additional maybe 10, 15 decibels of attenuation at the expected frequency where we expected to find a local resonance effect. And we also realize how well our experimental results agree with our homogenization model. Okay, so let's now wrap up the presentation with the conclusions. As a summary, the three main topics of the computational design of materials have been applied to the specific case of acoustic metamaterials. And as for the multi-scale model, a set of simplified hypotheses have been validated by computing the transmission loss of a locally resonant acoustic metamaterial panel. But in this regard, there's still room for improvement, for instance, in kind of refining these hypotheses in order to maybe tackle problems in a more general setting. Also, on the topology optimization side, it has been found that the present approach, though it worked for our purposes, still presents many challenges, especially in guiding the algorithm to select the appropriate resonance mode, which was, as I say, a challenging task. And in this regard, a more refined analysis and treatment of these issues would make the technique also applicable to more complex design goals and constraints, like, for instance, tackling multiple resonance bandgaps. Also, a side objective that have been achieved during this thesis, we have managed to introduce viscoelastic effects in the homogenization model, which allowed us to account for a more realistic material behavior, even though it has been observed that their effect in trying to enlarge the bandgap is somewhat limited, since it basically counteracts the effect of local resonance. And a topic for further research would be to study other damping models or unit cell configurations to see if they would allow for this dissipation phenomena to have a significant beneficial effect in conjunction with local resonance. Finally, an experimental validation has also been performed through 3D printed prototypes of a proposed design. But there is also much work to be done in this context, especially regarding the manufacturing process, as it has been observed that 3D printing is still a very novel technology, and there are actually still many challenges and limitations that need to be further explored. The specific scientific contributions of this thesis can be quantified in 3 articles on peer-reviewed journals, both in the computational and acoustics areas, with a total amount of 16 citations achieved so far according to Scopus data. And also, I would like to point out that research related to the present thesis has also been presented in several congresses around the globe, particularly 1 national congress and 3 international, including the last 4 congress on computational mechanics that was held in New York 2 years ago. As for future research derived from the thesis, there are 3 possible lines considered so far to explore. First, there is the sophistication of the model to account for even more realistic material behavior by allowing to relax the assumptions made, possibly by introducing block-floquet conditions in the kinematic relation, or, for instance, accounting by more complex material behavior, like, for instance, nonlinear effects. As noted previously, another research line would be to refine the topology optimization algorithm to making it usable in the design process of new prototypes that could be tested. And also in this experimental side, it would be interesting to keep exploring the limitations in the manufacturing process of this kind of materials and how our computational design tool can actually be exploited to assist in this task. Finally, since the model proposed is of general character, It could also be interesting to see if it can be adapted with minor modifications to the study of other types of materials, like for instance, electromagnetic materials. And to conclude this presentation, I would like to share with you a small experiment that we did with nearly 3D printed enclosure prototype. I warn you that this may be a little bit unpleasant for your ears, so please adjust the volume accordingly. We will compare the attenuation obtained with this box with homogeneous solid walls that has an equivalent mass to this other box composed of unit cells with resonators. And to do so, we cover this speaker emitting a pure tone at the internal resonance frequency of the resonators. So with this homogeneous box, we only get about 7 decibels of attenuation, which is barely noticeable with the recorded audio. But then with the metamaterial, we get more than 20 decibels of attenuation, which I'm sure your ears will be able to appreciate. And before I finish the presentation, I would also like to acknowledge the contributions from the Acoustic laboratory of the school, which allowed us to perform the experiments, and in particular to Teresa, who assisted us in all the process, and also to Hewlett-Packard for providing us with the prototypes for also the experimental tests. So thank you very much to all of you for attending this presentation, and I'll be very glad to answer any questions you have.